Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is Tensile Fabric Structure Design Updates in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Baca and Siska Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this GoToWebinar dialog box as shown here. We do our best to get to all questions, but if by chance we don't, we'll certainly send you a follow-up email afterwards. So as far as the content over the next hour today, I do want to begin with a list of new features and updates available in RFEM 6 specific to fabric tensile structures. So it's been a little while, a couple years since we last presented on this topic. So since then, we have certainly added some new features that will be relevant for our topic today. We'll then move on to our example structure that you see over here on the right-hand side, where we'll take a look at the modeling and loading workflow. We'll also talk about the application of the pre-stress loads for both the cable elements and the membranes utilizing the form finding add-on within RFEM 6. We'll further integrate our structure into our standalone program RWIND 3. So this will actually carry out a computational fluid dynamic wind analysis and a numerical wind tunnel to determine the wind pressures on the structure that we can integrate back into the main program RFEM 6 and to combine with the other load cases. So as far as the analysis, we will run the calculation and review all of our results, but we want to take this one step further to also carry out the design of the supporting structure. In today's example, we'll take a look at the steel member design according to the AISC 360, utilizing the steel design add-on. So it's really powerful in the sense that not only can we carry out the analysis and the design of these cables and fabric type structures, but also the supporting structure with the various materials and standards also available in RFEM, so an all-in-one software. And finally, at the end, we will take a look at the printout report and some various options available there. So we'll turn now to a list of new features available in the program, again, since we last presented on this topic specific to fabric tensile structures. The first is the new form finding surface load type SAG. So previously we only had the ability to input a form finding surface load based on the force or the stress input, but now there's a new option for SAG. We also have added a couple USA cable manufacturers, including Lexco and Connex, to both our cross-section and our material databases. Then we've introduced a new nonlinear orthotropic material that should be used for weave fabrics. And this is really powerful in the sense that it's using what we call a representative volume element underneath the hood. Now we'll go into more detail on this in the subsequent slides in our example today. We also have introduced a new surface load type called ponding. So this is really powerful for our fabric tensile structures in that the program will automatically determine the low inclination areas that are subjected to the accumulation of rain loads. When it comes to RWIND 3 and our CFD wind analysis, we can create a new material once we are in this program for permeable surface wind flow. So with information like the Darcy coefficient, the inertial coefficient, and the porous media length, we can set this as our material properties to allow wind to flow through the fabric structure. So this might be important for something like cable nets, for example. We also have introduced a new option called type of results when we do run our static analysis. So this allows the result display options to be toggled between the final state versus the difference to initial state. So do we want to include the results from the form finding process, or do we want to exclude them with the second option here, the difference to initial state? And finally, we have added the ability to export the deformed shape or the the deformed mesh to a DXF file. So this might be helpful for something like cutting patterns to again export directly from the RFEM 6 program. Okay, so we will begin with our model today in RFEM. And when we begin a new model such as this one, we are presented with our base data. The base data dialog box allows us to input in the model name. Under the second tab, we have the various add-ons. So for those of you that are not familiar with our program setup, RFEM is the base program that allows us to fully model the structure. We can access the materials and the cross sections from the various databases. But when we need a more advanced analysis, and in particular today, something like form finding, we would need an add-on, as well as the design capabilities. So we do want to carry out the design of the steel structure according to AISC. So we need to activate the steel design add-on. We will also integrate this structure with RWIND, our standalone program. So this isn't necessarily an add-on. Again, it's the standalone program, but we can integrate the structure, bring this into the numerical wind tunnel, bring those wind loads back in. And the final add-on I'm going to activate here is the nonlinear material behavior. Now, this is not required necessarily for fabric tensile structures, but the reason why I want to show it to you today is for that new weave fabric. You do need the nonlinear material behavior add-on for this. But I'll make a clear distinction when we will utilize this add-on specifically. Under the third tab for standards, we have the ability here to generate the load combinations automatically according to the AISC 7. The 2022 standard is implemented here, but we also have other standards available to us, including the drop down here for the NBC standard and other international codes. We will generate the wind profile for the RWIND calculation according to the AISC 7. And we will carry out the steel design according to the AISC 360. The new 2022 standard is also implemented in here, but of course the CSA S16 and other international standards. So here we are presented with our main graphical interface within RFEM. So many different ways to work in the program. We have our toolbar up at the top. We also have our navigator over on the left where all of our input data will begin to see that compile here. We also have the tables that we can work with. And for today's example, I'm actually going to begin creating nodes within the table itself. So I have here our nodes already generated within an Excel document. So the XYZ coordinates are already listed here. So it's easy enough just to select these, hit Control C. I'm going to go back to the RFEM model, and within the table, we can just hit Control V. So what you'll see are those nodes automatically generated here in the graphical space. Now, obviously our drawing grid is a little bit short here. So if we wanted to modify that, we could right click in the lower right-hand corner to click edit. And maybe we want to expand these points to 75 on either side of the origin in all directions. So now that drawing grid is a little bit larger for us. So we will begin here by drawing our first cable element. So we want to draw a new single member. And within the member type dropdown, we have a standard beam element, which is anything that's a beam or a standard column. But for a cable element, we specifically need to choose this member type here. Under the section, we will create a new cross-section from our database here. So we open up the cross-section library. Now it's very easy to choose a parametric section down here where we could input in the diameter and the program will calculate the cross-section properties for us. Alternatively, we have some cable manufacturers available directly in RFEM. So as you notice, we have several different options here for regions and manufacturers around the world. If we want to filter here to the United States, as mentioned, we've added in some additional manufacturers specific to the US like Lexco, Connex, and Teufelberger. So for today's example, we will choose the 1x19 here galvanized steel from Lexco. And as far as the diameter, we will choose the 5/8 common grade. We do also need to assign a material to this cross section. So very similarly, we access what we call our material database. And for cables, we want to use the drop down to filter to metal. And with the metal option, again, we have a lot of these same manufacturers here, including Lexco. We want to choose the 19 wire steel strand. Now, if you don't see your specific cable manufacturer in here, again, we could use a parametric round section. And we could always choose an existing material from the cross section or from the material library, and to come back here and click edit. Then we can turn on the user defined material where we can input in the material values directly given to us from the manufacturer. We can rename this one, and then we could use it for our RFEM model. For today, I will just use, of course, the material in the cross section directly from this manufacturer. So once we have input in the cross section and the material, we have the ability to snap to these different points here. So I'm just utilizing the nodes that I have already created, and we also want to snap here from the top point that will anchor down to the base of our structure. And the final cable element will actually be, instead of a single line, we'll use this drop down to draw a new arc element. And with the arc element, I can choose the two endpoints. I am going to reverse the orientation, but this allows me to directly input the radius of 10 feet. And I click OK. So now you can see here that we no longer have just a straight segment, but we now have this curved arc here for our final cable. So I'll right click to exit. You may notice the colors that are generated here. This is what we call member representatives. They are turned on by default, but we're not going to use them for today. So we can always go to our navigator under this second tab and go ahead and turn off the display of those. We also want to draw our members that will be our steel columns or our steel posts. So we will go back to the draw new member option, but this time we want to choose a standard beam element. And under the section, we will access here our cross-section library yet again. We will choose the circular hollow sections from our standardized sections, and utilizing the filters on the left, we filter to the United States, to the latest AISC database here, and we choose round HSS, and we are going to select 7.5 inch diameter by 0.188 inch wall thickness. Now we of course need to assign a new material for this one. So we will visit our material library, and under the drop down we want to choose the type steel, and we will choose the standard AISC 360 2022 A500 grade B. We click OK through these dialog boxes. And then we can choose whether we snap from top to bottom or bottom to top to create these additional two steel columns. So once I'm done with this, I'll go ahead and right click to exit out of this. We now want to move on to drawing our first membrane. So we would draw a membrane with the new surface option up here at the top. The problem with this initial drop down is that the surface is would be required to be in a single plane. And this is clearly not the situation here for our first membrane. We have double curvature. So instead we need to choose a new quadrangle surface with the drop down right next to it. The stiffness type is going to be set here to membrane. So the membrane can only take those tension forces, exactly what we'd like to see with a fabric tensile structure, and we do need to assign a new thickness as well. So we create a new thickness type, and within this dialog box, we'll immediately assign a material to it. So we visit our material library, just like what we've seen before, but we have the drop-down option for fabric materials. And there really isn't a whole lot of options available here in the database, but looking at these PVC options, we have 4 different material types. We could just go ahead and select this first one. Most likely what you're going to do here for your membrane is to select the material, and then again to come in here, just like what we saw with the cable elements, to choose user defined. And this will allow us to input in the information from the manufacturer specific to our fabric about what is the modulus of elasticity in the left and the right directions, X and Y. what is the thickness, and so on. Again, we could rename this if we would like, and then that material would be available to us for all of our fabric membranes. Now, alternatively, I also want to come in here. We'll go ahead and use the user-defined material, but notice that the material model is set by default to linear elastic. So this is probably sufficient in most cases for your fabric membranes. But if you remember back under the base data, I also enabled the nonlinear material add-on. So this now gives me the ability here to select this second option for a fabric, a nonlinear elastic material model type. And this enables a couple different tabs here up at the top, but this is specific to weave fabrics. So for this, I want to go back to the PowerPoint. We already touched on it, but we'll go into quite a bit more detail here with the new orthotropic fabric of nonlinear elastic material type. So this nonlinear material should be used to represent these weave fabrics. And ultimately, what we're doing in RFEM is we're using what we call a representative volume element, an RVE. And again, this is only specific to surface material types for fabric. It does require that nonlinear material add-on. But within this dialog box for the material, we will choose the weave pattern. So this will either be a plain weave, as we see indicated by this first image, or a basket weave indicated by this second image. And the entire purpose of this nonlinear material is to capture the anisotropic behavior, otherwise known as the direction-dependent properties, and the interaction between the warp and the weft fibers. So if we place a tension force in one orthogonal direction, because of the weave pattern, the fibers in the transverse direction are also going to be affected. So again, we're trying to capture this behavior. So we are implementing what we call a microstructure-based material model, again, with these RVE elements. Underneath the hood, what we're doing here is we're modeling these one-dimension elements to represent the fibers and the interaction between them. So internally, we're creating these inclined cables represented here by the green and the red lines. The vertical truss element, which is this blue line, is going to represent the distance between the fibers. We also have the ability to input in an optional shear modulus. This would be important for something like a coated weave fabric. But ultimately, we also want to get some information specific from the manufacturer, like modulus of elasticity in the X and Y directions. Again, this ratio of the RVE height to length is just going to represent the distance between these weave fibers and so on. It's important to know, though, that we're no longer using Poisson's ratio, but rather we're going to use this RVE. So it allows for the modeling of a simplified surface element rather than us having to individually model each fiber, which is unrealistic. So for us as the user, when we choose this nonlinear material model, we draw a surface and it looks like what we would see down here at the bottom of the screen. And depending on the mesh type, what's ultimately occurring internally, again, is the modeling of these one-dimensional elements here to represent all of the fibers and the distance between them. So quite powerful what we're able to do with this nonlinear material. Now for today, I am going to go ahead and choose just a standard linear elastic material type. So we won't be taking advantage of that nonlinear material, but that is an option if you would like to do so. So after we have set all of this information, we're brought back to the original dialog box where we can now click on the boundary lines to create that first quadrangle. So I'll go ahead and right click to exit out of here. And we do want to add in some supports at the base of our cables and vertical columns here. So we're going to draw a new support type, which we access in our toolbar. And we're just going to take advantage of one of the default options here, such as a standard pin support. I click OK, and I can highlight over these nodes here at the bottom. Now, if the support type is a little bit small, we can always right click to increase the size here and use this slider accordingly. So once these elements have been created on the right side, we're going to highlight all of them and we're going to use our mirror tool. And our mirror tool is exactly like what we would see in something like AutoCAD, where we can create a copy. We can mirror about the XZ plane and we'll mirror about the origin point. And we click OK. So now we see these same elements generated on the left-hand side. Now, before we continue making copies of this for the rest of our structure, there's one important thing that I want to point out is that when we right-click on this membrane, we can turn on the local axis system of the surface. And if we take a look at the local axis system, you'll notice that they're going in different directions here. And this really isn't ideal. We want to make sure to orient the local axes all in the same directions. It's important for loading purposes, but also how we interpret the results based on the local axes of surfaces. So the first thing that we'll want to do is to right click on our surface on the left, and we'll go ahead and reverse the local axis system so that now both z-axes are pointed up. Additionally, we can hold down our control key to select both surfaces. We double click to edit them, and we turn on the specific axes checkbox here. Under the input axes, we have the ability to direct the local axes to a point within the model. So we'll take the local x-axes of these membranes and we want to orient them through a vector within the model. And for me, I want this vector to be in the vertical direction right up through the origin. So I can input in a couple points here that represent this vector. And you'll notice when I click OK that both of the x-axes are now oriented towards this origin point up here at the top of my screen. So this will be beneficial now when we select all elements and we use our copy rotate tool. We want to create 5 copies here with a rotation angle of 60 degrees. And we will rotate about the global z-axis, the vertical axis, and the origin point, and we click OK. So now the rest of our structure is generated here. And if we go into an elevation view, notice that those x-axes are all oriented here to that center point. Okay, so I will right-click to turn off the local axis system, but the generation of our structure is now done and we're ready to move on to those pre-stress form-finding loads. Well, in order to do so, we access our load cases and combinations dialog box. Within the load cases, you'll notice that the program automatically generates the self-weight load case by default. I'll actually go ahead and override this with the pre-stress load case. I'll turn off my self-weight, and I'm going to change the action category here to self-straining force. So any form-finding loads when we're using the AISC E7 should be placed under the self-straining force. Now, alternatively, something like the NBC, we can use the pre-stress load case. But again, we would not want to place any form-finding pre-stress loads under the other action categories listed here. So once we have set up the load case, we'll go back into RFEM where we actually apply the form-finding loads graphically here to the structure. So we will begin with a new member load. And we'll bring up this dialog box, again, not to be confused with the option right next to it, which is a new line load that would be applied to something like a surface, but a new member load here. And under the load type, we want to select form finding. The form finding load type is only available because I have activated that form finding add-on under the base data. Otherwise, we would not see this option available to us. We have 2 different definition types here. We have either the geometric, which will allow us to input in the length, the unstressed length, sag for the cable element. Now, alternatively, we can choose a force. So if we'd rather put in the average force of a member, maybe the max or min force, the force density, this is also possible for that form finding calculation. For our example, I'm going to choose here the target length at 100% of the member for my initial cable elements, meaning that during the form finding process, I do not want the length to change. So then we need to assign this to the members graphically. And what will also be helpful is if we go to our navigator here under the third tab, we have some various viewing options where I can activate here the members by type to only turn on the cable elements. So everything else is grayed out here in the background except for those column elements. So moving to an elevation view, then this allows me to select here vertically, or all of the vertical cable elements graphically with my selection box. I will also go to a plan view here because I want to select the circular cable elements here at the center. And lastly, I'm going to select all of the cable elements here that attach to the shorter columns. So every other one, you'll notice that I'm selecting in the longitudinal directions, and I click OK. So I'm actually going to hit apply and next so that I remain within this dialog box, but you'll see those loads applied graphically here in the background. The next form finding definition for my cables is going to be set to a sag, and I'm going to set 12% here for the target relative member sag, meaning the program will try and achieve that sag definition for the calculation. So for this, I want to graphically select all of the exterior cables here around the boundaries that are spanning between the columns. Once we have selected all of these cable elements, remember that we also have these other longitudinal cables that are attaching to the taller columns. So once we have input in all this information for the member numbers graphically, I can go ahead and click OK, and we should see the loads applied to all of the cable elements graphically. So in a very similar manner, we want to apply the pre-stress loads to the surfaces. So we can apply a new surface load. And under the load type, we also set this to form finding. The calculation method has two options: the standard, which should be used for flat type membranes. Alternatively, we have here the projection method, which should be used for more conical or circular type shapes. And that's the scenario that we have with our example today. Now, in addition to the calculation methods, we have this drop down here where we can specify the membrane force, the stress, or as I mentioned in the PowerPoint, what we have recently added is the ability to define here the sag for the membrane itself. For our example, we will choose a force in both the radial and tangential directions because we do have this set to the projection radial method. And I'm going to set this as 0.07 kips per foot in both directions. But you can see how these are also dependent on the local X and Y axes. So it's really important, again, to orient our surface axes all in the same direction. The final input the program asks for this conical structure is what is the center point here, or this vector? For us, it's still passing up through the origin, so we can leave this as default. But if your structure was not placed at the origin here at the center, you could go ahead and modify that. And then we can graphically select all of our surfaces by canceling our visibility mode here and selecting surfaces 1 through 12. We click OK, and now we have that load applied to each one of the fabric membrane surfaces. So we can run a quick calculation here for the form finding. The program will automatically mesh the entire structure for us, and then it will run through this form finding shape based on the applied cable and fabric loads. So what you'll see here, if we turn off our loads, and it's a little bit overwhelming because we also have our mesh turned on. So we'll go ahead and turn off the mesh graphically. And maybe I also want to reduce here the deformation factor. But this is going to be the new starting shape of our structure with those applied form finding shapes found directly by the program. So we want to start with this shape before we apply any other static load cases to the structure. So let's talk a little bit about the results that are available here, again, just for this pre-stress load case. We're obviously looking at the global deformations, so this will be helpful just to ensure that we've applied all those form finding loads correctly. But we're probably interested in too the member axial forces. We want to see what those tension forces are within all of these cable elements. And so we see here these red tension forces indicated by a positive value shown here graphically. And notice that our steel columns are all in compression in this blue color shown here with a negative value. But in addition to the member axial forces, we were also trying to achieve a sag, a 12% sag with, for example, these external or these exterior cable elements. So we could turn on the local deformation of those cable elements. And if we were to calculate 12% of the member length, it would be pretty close to this deformation that we're seeing here. So a few different things that we can view with the members, but we also want to view the surface internal forces. And if we view the axial forces in the local x direction, we should see a range that's really close to that 0.07 kips per foot, because again, this is the form finding criteria that the program is trying to achieve based on those pre-stress loads. And if we view NY, again, we put in 0.07 kips per foot as our pre-stress load, and the range given here is fairly close to that, just with some deviation where it attaches to the columns, for example. Okay, so also just to mention verbally, we won't do this in our example today, but it might be quite common to place in here temporary supports during the form finding process. Perhaps we have temporary supports at the tops of our columns that will be used when we're applying these pre-stress forces out in the field. And then we remove them before we apply additional loads like live load or snow, rain, and so on. So how do we consider that within the model? Well, the first thing, of course, would be to apply a standard nodal support at the tops of our columns here. Again, I'll just verbally mention this. We would want to go into our load cases here, and we would rerun the form finding process considering these temporary supports, but then we would create a new load case. For example, our dead load, where we would activate our self weight here and we would choose the dead load action category. But we want to deactivate those temporary form finding supports. And we do so with what's called a structure modification. So we turn this on and we create a new definition type here where we could say remove form finding supports. Down at the bottom, we have a checkbox here where we can deactivate objects, and we get a new tab where I can tell the program, okay, let's go ahead and deactivate the supports on specific nodes. So I can choose here the node number, and then I could just graphically select maybe an elevation view, all of these supports that are applied to the tops of the columns. Again, we don't have them drawn here, but once we have all of those nodes defined, then we would just go ahead and click OK through these dialog boxes, and eventually we would leave this active for all of our other load cases and our load combinations. So the form finding support would only be active for load case 1, but we don't have that situation here, so we'll go ahead and remove that. It's also important for these load cases that we consider the initial state here from load case number 1, because again, this shape in the background is the new starting point before we apply any other loads or create our load combinations. We always need to enable this. So we'll go ahead and make a copy of this existing load case, and we will call it live load, and we will set the action category to live load. We'll go ahead and turn off the self weight here because we don't want to account for it twice, but notice the pre-stress is still the initial state set for live load as well. We'll create our fourth load case here, which will be for rain load with the action category set to rain load. And finally, our last load case is going to be wind load with the action category of wind. So Now that the load cases have been set, let us move on to the generation of the load combinations. Under the actions, this is just showing you all of the action categories that we have set from the AISC 7. When we're talking about the pre-stress form finding load case, this self-straining force, we actually don't want it to be included in the load combinations again. We've already set it here under the load cases as the initial state, so therefore under the actions, we can go ahead and deactivate this here, but we'll of course leave the other action categories set. Under the design situations, we create two design situations specific to the AISC 7. We have our factored load combinations belonging to this first design situation and our unfactored load combinations belonging to the second. But we do want to come in here very similar to the load cases to consider the initial state. So we turn on this checkbox, and under this second tab, we tell the program that for all of our load combinations, similar to the load cases, we want to use this load case number 1 as the starting state before we apply the loads and the load combinations themselves. So then if we jump to the load combinations, what you'll notice here is that for each load combination, we automatically have that initial state set. So we have our factored load combinations in orange belonging to that first design situation, and we have our unfactored load combinations here belonging to that second design situation. So now that we have the load cases set up, we need to actually apply the loads to the structure, similar like what we did with this pre-stress load case. So if we jump to the model here and we're currently looking at the dead load, we'll actually not apply any additional loads for dead load. We'll just assume that the self weight is the only load under this load case. So therefore for live load, we will go up here to draw a new surface load. And we want to toggle this back to a standard uniform force for our surface load. And we want to apply a load magnitude of negative 0.005, so just a very small load in the projected Z direction from our drop-down box. So considering the angle here of our membranes. And we can either graphically select it or we can simply tell the program this is applicable to surfaces 1 through 12. When I hit apply and next, we see that load applied in the background. And now I can toggle here to the rain load. So the rain load, we want to take advantage of this new ponding load type. So I'll go ahead and select this, but I'm going to go back to the PowerPoint to also explain this in more detail. So again, the entire purpose of this load type is to simulate the effects of rain or melted snow accumulating on multi-curved surfaces. So the minute that we draw in here a cable element or a membrane element, the program's automatically going to run all load cases and combinations according to a third order analysis. This is absolutely required for these type of elements, so we didn't have to set that manually. So inevitably, the different shapes of the structure are going to be determined according to this third order analysis, where we can actually view the low inclination areas that are prone to ponding. So I'm talking about the area as well as the height. But what else is interesting is that these shapes of this structure are going to change depending on the different loading combinations. So sometimes we have dead and live acting together, sometimes it's dead, live, and wind, and so on. So these ponding areas are also going to change, and the program will again determine this automatically for this load type only in the places where the rain can actually accumulate. So us as a user, we will see in just a minute how we input the density of this liquid, which will typically be water, and the program will automatically convert it to an applied area load at these different locations. And we'll see in our results, as you see over here on the right-hand side, that we can view this graphically, but we can also view the water depth and the water level, as well as the load magnitude at these different locations. So I think quite powerful what the program is doing, especially for these membrane type structures where accumulated water loads can present an additional load on these fabric membranes, but maybe not in all locations. So as mentioned, this loading type for ponding, we would input in here a specific weight. It's by default set to that of water, 62.4 pounds per cubic foot. Also, we are automatically going to assume that the full area as well as the height that can accumulate these ponding loads will be converted to a surface area load. Alternatively, if there's just absolutely no way that we're going to get enough precipitation to fill up this entire area, you as a user can turn on this amount of precipitation to maybe decrease that amount in inches per square foot. So if we don't want, again, this entire area that the program's determining is prone to ponding loads, we can modify that here. Now, again, we apply to surfaces 1 through 12, and we click OK, and we see this shown graphically here on the structure. But once we run the calculation, we'll go ahead and see what those ponding rain loads look like. Now we finally have here our wind load. And of course, if we leave this as an analysis type set to static analysis, just like what we saw with the other load cases, we can apply here the wind loads manually. But I'd like to take advantage of integrating this structure with our standalone program, RWIND. And we will now set the analysis type to wind simulation. We enabled this at the beginning of the example under the base data. But just to quickly explain, we can export this structure to this numerical wind tunnel to determine the wind loads. And why would we want to do that? Well, with these fabric membrane structures, they're very unique in their geometry. And in most cases, I believe that the code is not so clear on exactly the minimum wind loads that we should apply, again, for these very unique type shapes. So we probably have some guesses and some assumptions, but we can take this a step further to verify these assumptions in something like a CFD wind analysis program, just to ensure that the proper wind loads are applied to the structure. And then again, we can combine them with the other static load cases. Now, we're not going into a lot of detail into RWIND today. We have many other webinars that are devoted entirely to this topic, so I would refer you to them, but we'll just give a quick overview here. For example, we would want to set the wind profile according to the AISC 7. So we'll go in here and we could toggle this here to user defined, where we choose the exposure category from the AISC 7, maybe as chapter C. The basic wind speed can be set to a value, maybe 120 miles per hour, some other factors specific to the code as well. But to also clarify, we're not carrying out a wind analysis specific to the AISC 7 method. We are using computational fluid dynamics. We're just generating the wind speed entering into this numerical wind tunnel specific to the AISC 7. So now we see this wind speed as a function of the tunnel height here over on the right-hand side. So we click OK through these dialog boxes, and we can click OK to go back into the RFEM model, and we get a nice preview here of what this wind tunnel will look like with our structure. The quick thing that we need to do as well under Calculate Mesh Settings, here are the mesh settings for the static analysis in RFEM. This is set to 1.5 foot by default, but of course you can go ahead and modify that. But under the wind simulation, we also have some additional mesh settings that are specific to the CFD analysis. One thing that I'm going to do today is to go ahead and turn off this default option to consider the surface thickness. When we're talking about membrane structures, they are very, very thin. So it's not ideal once we're in RWIND to consider the thickness of that surface. It's not necessary. So typically you'll come in here and go ahead and turn that off. Now, we can run everything silently in the background for RWIND, but for today, I think it's worthwhile to go ahead and open up the program to see what this looks like. It's also important too, when we are opening up a fabric membrane structure in RWIND, that we have already carried out this form finding process. We don't want to bring over the structure, as you kind of saw here in the background, without the form finding loads applied, because of course the wind loads would never be applied to a structure without those pre-stress loads applied to both the cable and the fabric membranes. So RWIND is a standalone program. You can see it launching here. So we should see it pop up in just a minute. And again, I do want to emphasize, though, that it's not necessary that you have to pull open the RWIND program. You can certainly run everything silently in the background just as the load case in RFEM directly. So once we do see the program populate here, we see that form finding structure brought in, again, with all of the form finding loads applied. To also explain, we have our wind tunnel under this first tab here shown with the wind profile kind of passing from left to right here. And I can also activate our mesh, our shrink wrap mesh that is required for this CFD analysis. So those were some of the settings I was modifying in RFEM directly. Now this is a pretty coarse mesh. We could refine it further, especially where some of these members are connecting. But obviously the more refined the mesh, the longer the calculation time. So I will go ahead and pull open an already saved model here from my computer just because it does take a few minutes to run. But once we run this calculation in RWIND, we are presented here with the wind pressures from, again, the wind passing from left to right here through this numerical wind tunnel. So as I move my mouse cursor around, I see the value in PSF of that wind pressure applied to the structure. We can also rotate this on the underside to see some various values such as uplift. And again, we'll see that updating as we move our mouse cursor around. Same concept here with the wind pressure coefficients. The ISO lines or the ISO colors will not change here, but rather we just see the values that are modified for the wind pressure coefficient themselves. Now, if we're also interested in the wind pressure through the wind tunnel itself and not necessarily on the structure, we can enable some of these other flow field quantities. So now we have this slicer option through the wind tunnel that we can drag and drop, and we can view how those wind pressures are changing around the structure. Same concept with the velocity. So now we'll see the velocity in miles per hour is indicated by this color panel up here at the top. Again, with the ability to modify the orientation of these clipping planes as well as to drag them back and forth. Same concept here as well with the velocity vectors. So this is nice that we can see the direction and the location of the wind load on the structure indicated by these arrows here. And of course, we also have our streamlines. So the streamlines are going to show the particles moving through the tunnel, and we can go ahead and edit the streamline settings here by moving our box in the location here kind of more towards the center of the structure. I'll decrease the total number of points. So a lot of different modifications we can see, but now we have slightly less particles here where we can activate the flow animation. So this is really powerful in the sense that we can see, again, these particles, how they're deflecting through the structure. And under the tools, create video file, we can save a video file of the streamlines. We can attach it to our calculation package along with the RFEM model. And we've had clients tell us that this has been really unique in the sense that when they're submitting this calc package to their clients, the RWIND analysis just kind of takes it a step further, again, to verify those assumptions with nice colorful pictures and videos for the wind analysis on these unique structure types. But ultimately, the goal here is to determine the wind pressures on the structure. And we want to go ahead and bring these back into RFEM. And once we close out of our wind, we come back in here to the model, and all of those should be integrated together. Now, for me, I'm going to go ahead and open up an already saved model with those wind loads brought in. And once we do so, we would go to calculate all, and the program would cycle through all the different load cases and the combinations here. So we'll assume that we ran through those load combinations and the analysis combining the wind loads from our wind with the other load cases. So if we drop down here, for example, to load combination number 3, As mentioned in the PowerPoint, what you will also see over in our navigator is this new option for type of results. So we have here the final result or the difference to the initial state. And I think the best way to explain this is to jump here to the member axial forces, such as the tension forces. And if we zoom in here and maybe focus on this cable element, that's spanning here from the top of the column down to the base. I currently have this set to the final result, and my total tension force is 30.86 kips. This is including the form finding process, as well as the additional dead, live, and rain loads. Alternatively, I can toggle here to the difference to the initial state, and my tension force now drops to 27.17 kips. We're no longer considering the form finding calculation in these total results that we're presenting here, whether it's deformation or the internal forces for our members or whatever else it may be. So this is nice if you want to toggle between the two differences, including the form finding calculation versus excluding it from your results. Now, in addition to the member forces and tension forces for our cables, of course, remember we still have our steel columns that we can view the internal forces, maybe such as bending moments in the strong direction for those steel columns that would all be important for the supporting structure design. And jumping to our surfaces, remember we have these NX and NY forces that we check during the form finding calculation, but it's really important that we also check this for the various load combinations, because these values, these tension forces in the X and Y direction of the fabric membranes, are what we need to compare to the manufactured data to ensure that we're not exceeding their capacities. So we would do so in the NY direction as well. And all of this is available both graphically, but also in table format. We can view the results by surfaces. We could export to Microsoft Excel. The other interesting part about this load combination, if you remember, we had applied the rain loads, those ponding loads. So under the surfaces, we also have the shape tree that we can expand here. And we saw this during the form finding calculation, but we can view here for the rain ponding loads, the water depth. And I'll go ahead and modify this here to the initial shape. But these would be the very small areas for our structure today that could essentially accumulate those rain loads. So again, that area is determined automatically, including the water depth as well as the water level. And then we're going to essentially convert this into applied surface loads, which we can further see here with the option to turn on the distribution of loads. And within this option here, and I'll go ahead and collapse some of these so it's a little less overwhelming, we have the distribution of loads, the load using either our RWIND to see those applied loads or the ponding loads. And so now we can see the actual value in PSF, again, very small here. It's only 3 PSF at these locations. But if we change here to a different load combination, which also includes rain, you'll notice that we have a different shape on our structure. So inevitably, maybe there's some areas that are prone to ponding where others are not in comparison to the load combination before us. So again, can be quite powerful as our structure changes shape and those different applied loads for rain accumulation. Finally, under File, Export, we have this new option here under DXF2 that allows us to export the deformed mesh or the form finding shape to something like a DXF file that we can further open up in AutoCAD, for example, to carry out our cutting patterns. Now, this takes care of the static analysis with the fabric membranes, the cable elements, and we also saw the static analysis for our steel elements here. But we just quickly want to take this a step further to carry out the steel design within the steel design add-on. So for our example today, not going to go into much detail with this. We have plenty of webinars devoted to AISC as well as the CSA S16 that will further talk about the design here of these steel members. But just to quickly show you this, let me go ahead and enable all of the beam member types so that everything else is hidden or grayed out in the background. And if I select all of these elements and I double click here, again, these are just our round HSS steel members. I have the design properties turned on here, which is telling the program that not only do we want to carry out the static analysis, but let's design this supporting structure as well. So again, this all-in-one approach of designing the cables, the membranes, but also the steel members according to the AISC. So under the design types, we do need to set here an effective length. The effective length is just simply what are the unbraced lengths for the different stability failure mode types like flexural buckling. Now in this case, they are round HSS members, so are probably not so concerned with torsional or lateral torsional buckling, so we can go ahead and turn those off. But under the second tab, the program by default places these intermediate supports at both member ends. So this is just essentially assuming that our unbraced length is the full member length in both the strong and the weak axis direction for flexural buckling, and that's sufficient for our example today. So once this effective length has been input, we've addressed all of the other tabs specific to the AISC design. We drop down here to the steel design add-on. And we have our two design situations that we created with our load combinations where we assign the different limit state types. So strength limit state design according to LRFD will be applied to our factored load combinations, and our serviceability or deflection checks will be applied to the unfactored load combinations. Now, by default, the program will try and design all members here, but we can go ahead and turn this off. And what we would graphically want to do is to, again, select only our HSS members that are applicable for the steel design. Now we can run this calculation here. It takes a second because we already have the internal forces from the overall RFEM 6 model. We're just applying the AISC design equations to each one of these members. And you'll notice that we can view the design ratio by member results, and everything is synced up here in the table according to which member I'm looking at in particular. If we focus in on this column here and maybe chapter H, this combined flexure and compression check, we can visit our design check details. The design check details is new within RFEM 6 in that we can view all of the equations from the AISC line by line, including the variables and how we ultimately calculate this design check ratio. So trying to be as transparent as possible where these values are coming from, avoiding the black box software. You can add this to your printout report, these equations, and they'll also update with any model changes. So that's just a quick overview here of both the analysis and the steel structure design. In the last couple minutes, I just want to quickly go through a printout report example. So within our navigator, we have the ability at the very bottom option here to right-click to create a new printout report. It's also available up here in our toolbar. If we hover over this, we have the ability to create a new printout report here as well. And you'll notice we have many different options to turn on and to turn off within that printout report. If it's a little bit overwhelming, we can right click to collapse these into the individual folders and expand them further. But once you get this information set, it's really encouraged to create what we call a saved template. And that way you don't need to redefine this printout report template for every single RFEM model, but save as many templates as you like, and then you can pull open a template for all future RFEM models, again, rather than coming in here and individually turning on and off these options each time. Now, we also have some default template options that come with the RFEM program, such as the input data and reduced results. So we'll go ahead and use that for today, and I'll click Save and Show. So we'll see the progress bar in the lower left-hand corner creating this printout report for us. But essentially what's going to happen is a completely separate application will pop up here. And you can see that our cover page, we have the ability to include our company logo or any specific information about our project. For the overall image, if we wanted to edit this, perhaps we want to turn off the member representatives and maybe include more of the form finding shape, we can right click to edit it. Then we have our table of contents over here on the left. Now, again, if this looks a little bit overwhelming, just right click to collapse all these folders, and then we can take a look at them individually, such as the materials or the sections. And as I click on these, they'll automatically populate or sync over here in my viewing options on the right. We can also take a look at the steel design results. So if we jump to this, here is the steel design according to the AISC and table format for all of our steel columns. Now we have the ability as well to bring this over to a second monitor and to work concurrently in the RFEM program. And again, everything's going to update in real time with that printout report with any model changes. But if we wanted to quickly add images to our structure, for example, if we jump here instead of the steel design back to the static analysis, and I really am interested in viewing the global deformations here of this structure for all of my factored load combinations. And I want to add this deformation view to the printout report. Well, we might be thinking, okay, we could add an image to our printout report by going up here to graphics to the printout report, and we likely would need to maybe cycle through each one of these individual pictures, or sorry, each one of these individual load combinations one by one to create the picture and to kind of keep going back and forth. But alternatively, within this dialog box, we actually have the ability here to set the multi-print option. And the multi-print option gives me some additional tabs here up at the top. But before we do, maybe I want to modify the height here to, let's say, 50% rather than the full page height. So we'll see that update here that maybe we want 2 images per page. Then we have these additional tabs at the top for the multi-print. So I'm not so interested in printing off these first couple tabs, so I'll go ahead and uncheck them. But under my results, I am interested here in printing off the global deformations of my factor load combinations only. So within this option, I can click on the 3 dots here, and I will select only my factor load combinations to be moved or considered over here on the right-hand side. And I'll go ahead and uncheck this option under the last tab. So when I click Save and Show, the program will then cycle down here with the progress bar through each one of those factored load combinations to generate the images directly in my printout report. So we also saw the progress bar here as well. So once that is done, you'll see here under the static analysis results, again, all of those pictures automatically created for each one of those factored load combinations. These pictures will also, again, update with any model changes and once we rerun the static analysis. So certainly take advantage of that multi-print option for multiple load cases and combinations of where we're just trying to create maybe more than one picture. Okay, so we will go ahead and close out the webinar today. I will go back to the PowerPoint here. This presentation was recorded and will be uploaded on our website on the same webpage that you registered. I also have already uploaded the model that you saw today. And so for those of you who are maybe interested in RFEM, you do have the ability to access the free 90-day trial version of both RFEM and our RWIND. And with RFEM, it includes all of the add-ons that you saw today, plus all the add-ons that you also didn't see today, full capability for the total of those 90 days. If you have any questions about today's presentation or any of our products, feel free to reach out to our Philadelphia office with the contact information shown here down at the bottom of the screen. Our phone number is 267-702-2815, and our email address is info-us@delubal.com. So if you're further interested in maybe having a quick online meeting with our sales team, or perhaps you would like a demo in RFEM 6 specific to your project types, we'd certainly encourage you to reach out to our sales team, and that's myself included. You can reach us by visiting this QR code shown here. It's also in your handout in the GoToWebinar. Of course, you can also, again, reach out to that same phone number and email at the bottom of the screen directly to our Philadelphia office so we can coordinate that meeting further. We will have many more upcoming webinars. You can register at dluwell.com under support and learning webinars. As most of you know, you can register through email when I tend to send those out about a week before those take place. So just keep an eye out next month for the next webinar. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. The email is not instantaneous after this webinar ends. It usually takes 1 to 2 days to send those. So just keep an eye out in your email. If you did watch in a conference type setting, or you watched with a colleague and you yourself did not register with your own name and your own email address for the GoToWebinar, but you were here for the full duration, go ahead and email us at info-us@dluwell.com. Let us know who you watched it with, and we can certainly issue you PDH certificate for that as well. Again, our email info-us@dluwell.com if you yourself did not register but are wanting PDH. And with that said, I want to thank everyone for attending. And as always, we hope to see you at the next presentation. Thank you.